Alright, how are we doing? Let's get to the organic chemistry tonight, or this morning, I suppose. 2:10 a.m. by the way. Class in about 6 hours and 50 minutes. Can't sleep, so I guess it's time to do some organic chemistry. Gotta stay on top of this kind of stuff, unfortunately. So let's take a look at our first problem. Tonight will be oxymercuration, demercuration reactions. And honestly, I'm not really sure how they work, so let's review it a little bit. So what's going on here? We have our alkene. Here, let me turn up the hardness on the brush. We have our alkene. And what's happening? It's being attacked, or I guess it's attacking a mercuric acetate molecule. And apparently what happens here is that the mercuric acetate loses one of the acetate groups. It keeps the other one over here. And then we have what is called a mercurinium ion. And then next, water attacks this. It pops open the ring to give a water down here. Bam, just like this, with the mercury and the acetate. And then later we get a deprotonation step with this mercurinium part left over. Deprotonation by water. Get hydronium out at the end, and that's the first step. That's the oxymercuration. And then the demercuration step, well, we obviously take off the mercury, and the way we're going to accomplish that is by putting it in sodium borohydrate, I think is what it's called. Yeah, sodium borohydrate. Wait, is that what it's called? Good question. Whatever it's called, we end up getting our alcohol out with just this is replaced by hydrogen, so it's oxymercuration. So this is a way we can add a water. This whole reaction adds an H2O in the Markovnikov configuration. Okay. And apparently, I guess that's a better way of doing it than acid catalyzed hydration. Because with acid catalyzed hydration, you can form a carbocation, and that will result in rearrangements when you might not want them. So let's start with a problem. Okay, how about this one? Let us show the intermediates and products that result from alkoxymercuration, demercuration of one I can't spell, methyl cyclopentene using methanol. Using methanol as the solvent. Okay, so I didn't really go over this, but alkoxymercuration, instead of using water, it uses alcohol. Instead of using HOH like this, we use alcohol, which is like this, and we end up adding an OR, I think, instead of a contains an OR instead of an OH, I think. Instead of an OH. I think that's the only difference. Okay, so I spelled intermediates wrong, but that's okay. So let's look at this. 1-methylcyclopentene. So, penta, 1-methylcyclopentene, results from alkoxymercuration, demercuration, using methanol as a solvent. Okay, there we go. And so, I guess we should have both these things here, as well as the mercury. So what happens here? The mercury attaches itself to, what is it? Is it the least substituted? Or the most substituted? Okay, well I know that the OR group is attached to the most substituted because it's Markovnikov, so this mercury, I guess it doesn't really matter because, yeah, because, oh, I drew that wrong. Because it's gonna go like this. Like this. And that'll be the the intermediate, I guess. Here, let me draw this in a better way. How do I draw it in a better way? Jeez. Hg2 plus. There, I guess it's just Hg plus. Yeah, Hg plus OAC. And then we have to go right here. Isn't that a carbocation right there? Why do we say that it doesn't form a carbocation? You can tell I'm very knowledgeable about this reaction. Oh, because we keep this thing here. That's right, it's like cyclopropane. Propane, I mean. So that's cool, I guess. And then, what next? And then we add... oh, I guess next this attacks that, I suppose. Oh, and then... right. I'm learning. Okay. I'm learning. So now we've got... this, where it's Hg plus OAC, like this. Okay. Alright. And then water comes by. And oh, what does water do? I guess it attacks this. Jeez. Jeez Louise. Dear God, I have no idea how this mechanism works. Oh, it's not water. What am I thinking? It's NaBH4. And how this works is a mystery to me. I don't think my textbook even mentions how this works. Which is kind of stupid, not gonna lie. Yeah. Yeah, really stupid, actually. Huh. Okay, well, let's look at the answers here. What's going on here? So mercuric acetate adds to 1-methylcyclopentene to give the cyclic mercurinium ion. Okay, sure. Considerable amount of positive charge in the more substituted tertiary carbon atom. I'm not sure why, but I guess, yeah, sure, I guess that makes sense. Methanol, because all the substituted groups are electron donating, so I guess the positive charge wants to go there. Methanol attacks this carbon from the opposite side, leading to anti-addition. The reagents, mercury and methanol, have added to opposite faces of the double bond. Okay, so that means that whenever I added this, I should have picked a direction. Like, so if we said it'll end up being like, what, like this? Oh, this is the wrong product too. What am I doing? What, like this? Okay. Oh, and then there's a deprotonation step. Because this is a really strong acid, I guess, because of the, lots of positive charge. So then we get this thing. Okay. Okay, and then sodium thing comes by and it converts this to this. It's both enantiomers, I suppose. It's both of these, I guess. And there's also this, I guess. I'm just completely wrong here, aren't I? Oh my god. Jesus, okay, let's redo this. Let's redo this and figure out where did I go wrong? Okay, so 1-methylcyclopentene is like this. And then we add HgOAC. I think there's a lone pair right there or something. No. Goes like this, like that. And then we end up getting a thing like this. Alright, so far so good. Okay. And then we have methanol, which is a strong, or I guess this thing is, it's gonna attack, it's gonna attack what? What does it attack? Where does it attach itself? Attacks the carbon. Oh, that's right, because the carbon has a partial positive charge. And then attacks this carbon. And now this thing goes here to give the mercury some neutral charge, I suppose. And then we have anti-addition. HgOAC. I guess it's like this. Or something like that. I don't know, I'm not going to draw the lone pairs, I don't really understand them. And then there's a deprotonation step. Oh god, I can't draw. There's a deprotonation step, like this. It takes the hydrogen off. And this molecule. And then NABH4 comes by, and we turn it into one of these things. Okay. Jeez Louise. So, I don't really get what this sodium thing's here for. It replaces this thing with hydrogen, but I don't really understand how. It's supposed to be a reduction reaction, I think, but that doesn't make any sense with me. That doesn't make any sense. Okay, so apparently this is what's going on. Apparently what's happening is, let's say we have a carbon here with this oxygen, this alcohol thing that we have at the end. And then we have NABH4. Apparently this happens in like a basic solution. And what happens is that we get, what the fuck? Wait, what? I don't understand. Oh, it switches its hydrogens out for, oh, whoops. Okay, it's 4 of these, by the way. 1 of these and 4 of these. But yeah, switches its hydrogen out for the hydroxide. So there's 4 of these things, I guess. For the hydroxide, it also gets 4 mercury metals and 4 acetates. Now the question is why? Like, who came up with this? I don't know, whatever. Next question. Let's see the next question. I kind of understand it now, a little bit. So, propose a mechanism for the following reaction. Okay. Now, of course, we have to make the reaction. This reaction is CH3 bonded to CCH3 double bonded to CHCH3. Okay. And this reacts with the mercury acetate thing, as well as ethanol. And then that'll result in us getting a CH3 here, another methyl, bam, bam, with ethanol at the bottom, and the mercury acetate reforms. Okay, yes, 90% is this. Okay, I don't know what the 10% is, but whatever. So let's see. Let's first draw our molecule. 1, 2, bam, bam, bam. I guess it doesn't really matter if it's cis or trans. So let's do cis, I guess. Or is this cis trans? This is what? Z. I don't know how to classify this. Geminal. That's what it is. Okay. And so what happens here? We have Hg, OAC2, and the ethanol. So what happens here? We get the cyclopropane looking kind of thing with this. And then it goes with the ethanol. And then the ethanol goes on the most substituted carbon. So we have no substitute carbon. It'll be like, ooh, thinking how to draw this. It'll be like this. We'll have the ethanol like this. The methyl out like that. Sorry, into the page. So then, yeah. This will be the resulting intermediate. And then, yeah. So is this right? No, because I got one of the methyls wrong. Okay, that's embarrassing. And then, what is that? Is that match up with what we got? Yes, that is match up with what we got. And then we have to give the structure of the product that results whenever this intermediate is reduced by sodium borohydride. Okay, so that's what the molecule is called. Sodium borohydride. Okay. So I'll just have it like this. Bam, bam, bam. 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 Stereochemistry does not matter here. Yeah, it doesn't matter here. Cool, because this thing can rotate. Right, cool. Let's see if I was correct. Looks like I was correct. And I'm the smartest chemist that's ever lived. Of course, I already knew that, but this is just confirmation, and validation's always nice. Okay, so let's predict the major products of the following reactions. I'll write it down, I suppose. No reason. I guess I should just draw them, because it'll make me better at recognizing, I guess. Okay, so that's the first reaction. Second one is that treated with NaBH4. Okay, so I feel like I know how the next problem's gonna go. So for heptene. Oh god, a heptene. I can't draw those. GOAC2 in ethanol. That treated with NaBH4. Okay, so let's do it. Okay, so 1-methylcyclohexane. Bam. Bam, 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 bam. Bam. Plus HGOAC. Let's see if I can do this in my head. So what we're gonna do is we're gonna pop open the... Wait, this is the opposite of doing in my head. What am I doing? And then it's gonna be in water. I guess I'm not gonna do it in my head. Or I'll do it without drawing arrows, I guess. And then it's gonna go to this thing right here. Actually, what's the... Yeah, no, whatever. I'm indecisive. And then I'll pop open the thing there, and we'll get a nice looking mercury looking kind of thing. And then whenever it's treated with NaBH4, we'll end up with this thing. Well, that was easy. What do you call this? Call this 1-methyl heptan. Whoa. Cyclohexane 1-ol. I think. Yeah, nice. Okay. Now, next one, we're going to do 4-chlorocycloheptene. Okay, I don't actually know how to draw heptene, so let's give it my best shot. Oh, I feel like I'm already fucking up, or messing up, whatever. I can swear it's organic chemistry. Oh god, like this. 1, 2, 3, 4, 5, 6, 7. Nice. Okay, 4-chlorocycloheptene. Okay, 1, 2, 3, 4 chloro, and we add the. Oh, I don't know how this interacts with. Wait, no, I don't really know how this interacts with halogens, so I guess I'll find out when I look at the answer key after I try it. Let's see. So now we get bam, bam, our ion here with our halogen down there, and now methanol is here too. Which one's the more substituted side? Yeah, there's no. Which one's better for this to go on? I'm guessing this one right here. I bet this one has more partial positive charge because the positive charges want to go more there because this thing is electron grabbing. Or maybe I guess that would mean it goes over here. I'm just gonna pick one. I'm gonna pick the one that's closest to the chlorine. Yeah. So now we have this thing. A halo alcohol. I don't think these exist. And then what water comes by, takes this away. I forget what comes by to take it away. Cl, OH, whatever the case is, we get this strange molecule. Whenever, oh, sorry, not water, what am I saying? It's NaBH4. There we go. And what we get this thing? I feel like that's very incorrect. But apparently it's correct. Okay, well, it's kind of correct. I have to draw out the stereochemistry, of course, like this. But it actually turns out that we get both of these products. So there's no bias. There's no bias at all, actually. My electron pushing theory was completely false. Of course, we also get the enantiomers. Hg, OAC. Bam, 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 bam. Bam, bam, bam. Okay. It's good I'm learning this now instead of on the test day like I did last time. Yeah, that was not a great experience. You know, here where I live, when I was taking my exam, we had power outages when the exam was happening, like last week. Power went out 3 times during the exam, so that was really cool, and I really appreciated that. Really made my life easier, especially when taking an organic chemistry exam. Whatever. Okay. Ooh, I like these. I like these problems. Show how you would accomplish the following synthetic conversions. I'm a great big... I really like these problems. I mean, maybe I'm not the greatest at them, but they're this is exactly what I thought chemistry would be like whenever I was a little kid. So imagine my disappointment when you do Gen Chem, and it's literally just like, it's just math. That's all it is. It's literally just math. And it's so boring. And I never want to do it again, ever. I hate Gen Chem. It's the worst class I've ever taken. So boring. Labs are boring. Course materials, like, mind-numbing. And it's all just algebra. Well, no, I guess technically there's calculus too, but you don't need to know it. You literally don't need to know it. It'll help, so you don't have to remember your rate conversion, like rate law forms, I guess. But aside from that, it's just all algebra. And I mean, I wish this class was that easy. But I guess that's just the price to pay to actually do something interesting. Explain why acid catalyzed hydration would be a bad choice for C. I mean, I have an idea of why it would be a bad choice already, but I guess we'll do the problem and see if my prediction is correct. I bet it's gonna have a rearrangement, and it's gonna screw up the product. So we have but-1-ene, and we have to turn that to 2-methoxybutane. 1, 2, 3. What, methoxy? This? Is that what methoxybutane is? I'm just gonna assume. So this probably, we want to use the mercury thing, plus methanol. And so the first step here, it'll get us to this lovely thing that we keep saying. I don't know what, mercurinium. That's right, that's what it's called. Our lovely mercurinium. And then we have to, what's next? Oh yeah, the methanol adds itself to the substituted, and like this, and we get this thing, and I suppose also the enantiomer, although I'm not so certain that this is even an enantiomer. I guess it is. I guess there's an enantiomer of this out there. Where it goes like, I'm just gonna say both enantiomers. No, it's cheating, and I want to get better, so let's have it like this instead. Bam, bam, bam. And then, by the way, I drew this wrong. Well, I guess it's not wrong. It's just not rotated correctly. Whatever. I don't care anymore. And then we'll have HG. I'll fix it in the enantiomer. God, this class is such a struggle, especially when you're a dumbass. God. And then we have to... NABH for it, giving us this molecule that we love. Yay! Yay, I love it. Okay. Alright, next problem. 1-iota-2-methylcyclopentane. So we have... is this layer 2? Okay, yes. So now we have cyclopentane, 1-iodo, 2-methyl. So 1-iodo, 2-methyl, cyclopentane. Whoa. Is it pentane or pentene? Wow, okay, yeah. 2 1-methyl cyclopentanol. Okay. Wow. This is pretty advanced. Because I don't know how to do it in one step. Okay, I don't think we can do it in one step. How can we get an alcohol from an alkane? Is there a possible way to get an alcohol from an alkane? I'm sure there is, but there isn't really anything that comes to mind. Let's see. What can I do to an alkane? I can dehydrohalogenate it to make an alkene. I can do a substitution reaction. I do an SN2 reaction. Oh, maybe I can do an SN2 reaction with an alcohol, but that would get me to that would get me to have the alcohol. Okay, so what if I have SN2 with wait, no, you can't have SN2 with an alcohol because it's a weak nucleophile. If we have SN1 with, let's say, methanol, then this will be the carbocation, and then there's gonna be a hydride shift. There's gonna be a hydride shift like that. You know, SN1 is looking pretty promising. And then and then what? And then hopefully it substitutes onto here. Then substitutes onto here, I guess. So that's a possibility, I guess. But somehow I feel like they want me to do some alkane chemistry. The thing is, if I do it like this, it'll I mean, there's also the possibility. Yeah, no, I guess that's fine. You have to do SN1 with a methanol, but I guess there's the possibility of it being an elimination reaction. So then when it goes like this, we'll have our methyl right here. Once we have it like that, we can do our whole mercuration demercuration thing that we want to do with methanol and also NaBH4, and that will get us our desired product as well. Is there any other possibility? Yeah. What else could happen here? Yeah, I think that's how we would do it. Let me think. What else can we do? We can whatever you call it. Dehydrohalogenation. Although I guess, wait, dehydrohalogenation, is that the same thing as the E1 reaction I just drew? I think it might be. I think it might be. Yeah, I don't really see any problems with my mechanism. Let's check it out. Let's check out the answer. I mean, I'm sure there's so many problems with it that I can't even believe. Alright, 8, 9. What do I want here? Okay. Obviously they want me to do this version. Sorry, not that version. Let's see. Oh, wait. Okay, well, clearly I'm just a dumbass because you don't do it with the methanol. You do it with hydroxide to try to do what I was doing. Wow, I'm stupid. Yeah. What would happen if I added a methyl here? Or sorry, am I dumb? What's the E1 reaction? Man. I'm getting all my reactions confused. Uh, uh. Why am I doing? Wait a second. I know why. Okay. Oh wait. No. Do I know why? Uh. Oh God. Oh God. What am I doing? Where's dehydrohalogenation again? Well, dehydrohalogenation can be either E1 or E2, right? One iota, 2-methyl cycle pentane. Oh man, this doesn't really matter. So apparently what it wants me to do is go through like this with also, oh yeah, lots of heat as well. And then I guess we'll undergo an E2 reaction. What am I doing? This is a single bond. Jesus Louises. Yeah, so what? This. How's this go again? This. There we go. Okay. This attacks one of these. It grabs one of these, and it goes like this, and it goes like this. Okay. So that's an E2 reaction. And then we end up getting this plus a water. That's nice. Yeah, so then, and then we can do our mercury acetate thing plus an NH4, and then we're gonna get the desired product. Yeah, okay. I guess E2 is better than just E1. Because if we do E1 like this, with lots of heat to encourage E1, we're gonna have this. I mean, iodine's a really good leaving group, so this wouldn't be unfeasible. And then we would have to have a hydride shift here. Or I guess do we even need a hydride shift? We have 2 H's. Yeah, I guess it would necessarily have a hydride shift because it's a carbocation. So if we just encourage elimination like that, then which hydrogen does attack? I mean, I guess it doesn't really matter because it results in the same thing, but I wanna get this right. What hydrogen does this attack? I guess either one of them. Yeah, I guess either one of them is why we have so much stereochemistry with. Okay, well, I'm gonna ask. This is a question I need to ask my TA because I don't understand. Okay, cool. So 3-methylpentoenine and 1, 2, 3 to 3-methylpentan-2-ol. Okay. Wait, how can you have pentan-2-ol? I could have a 2, 3. There should be at least a 1. Wait, is that a misprint? Isn't that the same thing as 2-methylpentan-1-ol? Oh, it's not a ring. It's not a ring. 1, 2, 1, 2, 3, 4, 5. Okay. So pentan 2. Oh, Jesus. How does this happen? How does it... Whoa, how does it pop open the ring? Oh, God. Oh, God. Well, yeah, what happened to the ring? I don't know any reactions that can open up a ring like that. I know ring expansion. Like, Okay, well, how do I break open the ring? Oh, I know why. I don't need to break open the ring. I just can't read. That's the problem. That's my problem. Or one of my problems. I can't read. Oh man, I wish I could read. Okay. So then, yes, I think this is pretty clear. We want to use our fancy mercury reaction with what? In water. And that'll give us our nice mercurinium ion, OAC. Bam, 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 bam. And then that'll give us our bam, 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 bam hydroxide in the most substituted spot, which is this one. And our mercury, it doesn't have the plus charge anymore, is out here. And then NaPH4 comes by, and we get this thing. Yay! Now, as to why acid catalyzed hydration would be a bad choice for C, let's look at acid catalyzed hydration first. Or now, Jesus. So dilute acid. So what happens here? We have a carbocation, or this thing. Oh, I know we're gonna form a carbocation. This is going to, or is it? Is it gonna attack like this? Ugh, I don't remember my acid catalyzed reaction here. Fairly certain the yeah, I think it takes one of these away. Okay, and then what do we get? We get a carbocation like this. Okay. Like that. Oh, but we gotta remember there's other hydrogens lurking around. And the other hydrogens, you do a hydride shift. And then now our poor molecule is like this. And how does it? Wait, God, I'm messing up my steps again. I don't know how catalyzed hydration works. I did it yesterday. What's the step after this? Wait, we already reacted with the acid. Oh, right. Now we have to react with the water. Goes here. And then we get a bam, 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 OH2 plus. And that gets a deprotonation step by water. Bam, bam, bam. And then we end up getting this molecule. Yay! Woohoo! Nice. Which is not what we want at all. So that's why acid catalyzed hydration is a bad choice for this one. Okay, now I feel like I need to do a little review of what you can do to alkenes so far. What can we do to alkenes? So we have our poor little alkene here. What can we do? I've learned so far about... What have I learned about? Well, okay, we can do acid catalyzed hydration. Here, let's do it like this. That'll end up giving me a what will that end up giving me? It'll add it in the Markovnikov position. So it'll be something like, oh Jesus, like this. Okay, that'll, is that right? Does that look right to me? At the OH in the on the right hand side. Yeah, because it'll add the water on the the carbon. Okay, so yes. So that's Markovnikov. And then we can also do a bromination, a halogenation, I should say, and that'll add as well. Oopsies. That'll add as well to this side. But then we can also do one with the peroxide. It'll actually add it to the opposite side, I think. Yeah, it's definitely going to. You can add like this. Like this, right? Let me think about it. First, it's going to abstract a hydrogen. The bromine's going to first abstract a hydrogen, right? Yeah, I think. Look at what's the mechanism for this again? Radical addition. It adds to the bromine first. Right, okay, yeah, that makes sense. And this is anti-Markovnikov. And then we can also do our this thing to it, and that'll add it'll either make an alcohol like before, just like the acid catalyzed version, or it'll make an ether. I think it's an ether. Like this. Okay. So that's what we can do to alkenes. Oh, I messed up. Now what can we do to alkane? Whoa. What can we do to alkanes? We can do a lot of fucking stuff to alkanes, actually. Way too much stuff. I literally don't even know what we can do to alkanes. There's so much stuff we can do to alkanes. Oh god, oh my god, what can we... Everything. Let me look it up. There's so much stuff we can do. Oh, we can do a... Well, I guess it all depends on what's on the alkane. So if we have a halo alkane, oh sorry, we can do a free radical bromination, or free radical, whatchamacallit, free radical halogenation. And this is pretty stereospecific, I guess. Oh, sorry, it's pretty regiospecific. So if this is an H right here, it's gonna add on to... Oh god, where would it even add on right here? Nowhere, right? Oh no, I know where it would add on, I think. Which one would it add on to? God. I think I'll make it easier if it's like this. Yeah, so then it'll add on to our site over here. So that's one thing we can do. We can turn in an alcohol somehow, I'm sure. I don't know. I think we have to go from here to... How do we turn in an alcohol? We would have to do some sort of... oh yeah, we have to do an SN1 reaction. Or no, SN2 reaction. So like something like this. With a polar aprotic. So actually no. Here this is a tertiary substituted carbon, so it should automatically go to E2. So we end up getting this thing. Remember the stereochemistry switches. Yeah, so then what can we do with this? We can do a dehydration with acid. Then we end up getting... Oh, this is a nice flowchart I have here. What else can we do besides this? Oh, we can turn it into an ether somehow. But how can we turn it into ether? We have to have an alcohol like this, and then that'll end up being what? Will it be an SN1 reaction? I guess it will be an SN1 reaction. So then we have like this eventually after like a step, and also the enantiomer. I think this is Williamson ether synthesis, although I could be wrong. How do we get Williamson ether synthesis? It's a SN2 reaction. Shit. Well, that's awkward. Oh, because this is why. Because it's not that at all. It's E2 reaction, so it'll be R O minus, and then like a sodium. Right, okay, so then, okay, that makes sense. That'll be a O R, and then there's O right there. Okay, cool. So we can do that to alkanes as well. What else can we do? I feel like most things for alkanes are actually just haloalkanes. Yeah, I think this is all the reactions I know that can happen that we can use to turn like just like a regular alkane into. We can turn an alkene, we can turn it into an alcohol, or we can turn it into an ether after we've turned it into a haloalkane. Yeah, yeah, I think that's it, really. Huh, that's cool. Yeah, so that's it for me tonight. It's 3:12 a.m. Gotta go to sleep and go to class tomorrow, hopefully, if I wake up on time. Hopefully I'll come back with a better knowledge. So yeah, nice time tonight.